Hi everyone, this is Dmitry, I'm a professor of mechanics. Today I would like to discuss with you a module that I wrote using the Wolfram language. This module helps me to solve one of the key problems in the mechanics of materials, namely to solve the beam bending equation. Let's first look at how the module works, taking this statically determined beam as an example. The beam has two supports, a pin and a roller. The loadings are the following: two uniformly distributed forces, a couple moment, and a concentrated force. Let's enter the beam parameters, like this. It's easy to see here the supports, the loadings, some numbers, and so on. Using the BeamSolver function, we automatically find the support reactions, make a differential equation of the beam with boundary conditions, and solve this equation analytically. Let's do it. Okay, it takes a few seconds to solve the ODE. As a result, we get some association, which I called my beam solved. Let's display the list of keys in our association. Here we can see not only the familiar loadings, supports or numbers keys, but also several new ones added during the solution. And the loadings key now gives us not only active loadings, but also the analytical expressions for the support reactions. In addition, we can print the fourth order differential equation for our beam and also the boundary conditions. All this stuff was generated automatically. Now let's move on to the most interesting part, the deformed shape of our beam. We take the solution key. The fourth element here is actually our deflections. It's easy to guess that the other three elements are the slope, bending moment, and shear force. You can see that the expression for the deflection is pretty complicated, but it's a single analytical expression, which is great. Okay, let's put in the numbers. This is what our support reactions now look like. In our example, these are two forces with different directions. Here is the beam equation, and this is the desired deflections function. We can immediately plot this using the built-in plot function, as I just did. But what if we take instead the special designed bplots function, which shows us all we need? Let's do it. It shows the distribution of the shear force, the bending moment, the slope, and the deflections. The arrangement of these plots one below the other gives a better understanding of the relationship between the functions. You can see that each previous curve is the derivative of the next one. This is exactly what the beam theory states. Using the beam max value function, we can easily find the local and the global extrema for any diagram. Here, for example, I found the local extrema for the bending moment and deflections. First the local ones on the interval from 4 to 5.5, and then the global ones. Now let's take a closer look at the most important feature of the module, the analytical solution of the beam equation. This allows us to modify the parameters of the beam and recalculate it very, very quickly. For instance, let the force P slowly move along the beam. The position of the force relative to the beam's left end is determined by the parameter x sub p. Using the built-in manipulate function, it's easy to construct an interactive plot showing how the beam shape changes as the force moves. For simplicity, I'm not showing here the loadings that remain unchanged. Let's move the slider. Isn't it great to just move the slider left and right, immediately getting all the shapes? Now let's discuss some technical details and see the inside of the module. Remember, in order to solve our problem, we first need to enter the beam parameters, then calculate the support reactions, then find the boundary conditions, then make and solve the beam equation, and finally plot the diagrams. This is why the code is divided into 5 corresponding sections. Okay. This module is designed to work with only statically determined beams, simply supported, cantilevered or overhanging. The loadings can be concentrated forces, couple moments, or uniformly distributed forces. The supports can be pins, rollers, or fixed end. So, in the first section, you see several predicates that allow to determine which load is applied to our beam and which support it has. All the data for a beam is stored as an association. The code in the second section calculates the support reactions. Well, nothing particularly interesting here, simple moment equations about 2 points and the solution. Let's move on. The boundary conditions depend entirely on how the beam is supported. The code below takes into account all the cases shown in this figure. The central part of the module, its heart, is making and solving the beam equation. This is what it looks like, the well-known fourth-order differential equation that relates the deformation of the beam y of x to the function w of x, which describes the distributed loading on the beam. This loading can be caused again by concentrated forces Fi, couple moments Mj, or uniformly distributed loadings Qk. At that point, the support reactions are already known, so they are included in the Fi or Mj arrays. You can see here that the w of x function contains some tricky functions like Dirac delta prime, or Heaviside theta. This stuff helps us to represent the loading on the beam as a single function of the x-coordinate without splitting the beam into regions. This simplifies the solution process a lot and reduces the amount of code. Solving this differential equation with the dsolve value function, we get the function y of x, which describes the deflection we need. Its first derivative gives the slope angles, the second derivative multiplied by the bending stiffness gives the moment, and finally the third derivative is the shear force. The final section doesn't contain anything really complicated, just some code for plotting diagrams and finding the extrema. Okay, it was a short overview of the BeamSolver module designed to calculate the deflections of beams as single analytical expressions. And as you saw, this tricky problem can be solved with just about 100 lines of code, thanks to the power of the Wolfram language. Have a nice day, and I see you later in the next video.